Okay, now again, I'm talking about the electromagnetic waves perpendicular to B naught. But here, the second scenario I'm going to consider that E1 is perpendicular to B naught. So if E1 is perpendicular to B naught, the electron motion will be affected by the magnetic field, and the dispersion is going to change. Now, these wave in this case, by in order to analyze this situation, we can take as before. I'm going to mention B naught is in the z direction and K is in the x direction. And we, in order to make this happen, that E1 is perpendicular to B naught and K is perpendicular to E1, which is the condition for the electromagnetic waves, we can take E1 as in the y direction. But here, when we analyze this kind of situation in these waves, we came to know that these waves are rather elliptically polarized instead of plane polarized. When these waves propagate into plasma, it develops a component in the x direction, that is Ex along k. That means these waves becomes partly longitudinal and partly transverse. So this special character of these waves, because of this special character, we call them extraordinary waves. Or X waves. So as these waves have electrostatic part, also the electromagnetic part, so these are extraordinary. So in order to analyze this case properly, I'm going to take E1 like that, but I'm going to consider both X component and the Y component. This will help us, to analyze this wave in order to understand what is happening when the electromagnetic waves are traveling perpendicular to B naught and they have electric field component perpendicular to B naught. So by keeping this in mind, I'm going to solve the equation of motion. So keep in mind that now the electric field is in the x and y component, y direction. B is along z and k is along x. Or I can make a graphical representation that let's call it x, y, and z. So my B naught is in this direction, my k is in this direction, and the electric field is going to be in this. So I'm going to erase all these terms and then we will consider this geometry. So the electron equation of motion that we have already discussed before, that it is going to be electron equation of I am talking about the linearized equation of motion of electrons. So it is okay. Now this is the vector equation, and I'm going to write the x and y component of this equation. So when we take Vx, we are going to have here Vy V naught because of this geometry. And then when I take here Vy, I'm going to have Vx and V naught minus. So I'm going to write it in a compact form. Vx instead of v1x, I'm just writing vx minus iota e over m omega ex plus vy b naught, and then vy equals minus iota e over m omega ey minus vx b naught. Now by solving these two equations, we can get an expression for Vx and an expression for Vi. It's very simple. By just take this value here and substitute it here and then solve this equation for all Vy. I'm writing only the final result of by solving these equations. So we have Vx equals similarly I can write for Vy So these are the two equations that we get from the equation of motion. Now the second will be the use of the Maxwell's equation that we have already done in the previous lectures. That we solved the Maxwell's equations for the electromagnetic waves passing through plasma, and we came to know about that there is a J1 term that is going to be there for the plasma. So keep it in mind these two terms that we are going to use, and now I'm writing the Maxwell's equations that we will solve to find out the expression for the electromagnetic waves, the extraordinary electromagnetic. So from the Max, okay, this is what we will get from the Maxwell's equation: omega square minus c square k square e1 plus c square k dot e1 equals iota m naught e omega by epsilon naught v1. So this is a vector equation. I can write the components of this equation. So by writing the let's start with the x component. So we have omega square minus c square k square. Keep in mind this geometry. So we have ex c square k, which is in the x direction. Now k is in the x direction, is e is in x and y direction. So we will get kx and ex. Iota m naught e omega by epsilon naught vx. This k square is basically kx square. So this term is going to cancel with this term, and we are left with omega square ex equals this. Similarly, we can write the y component of this equation: omega square minus c square k square ey. Now there is no y component of the k vector, so this term will be dropped, and we have iota n naught e I so not vy. Now we have these two equations, and we have the values of vx and vy from these two equations. So I'm just going to substitute these vx and vy here, and then write the equation in terms of ex and ey. So I'm going to erase that, and I'm going to write it again for ex and ey. So just remember that now I'm going to substitute the value of vx here and the value of vy. Okay, this is what we will get when we substitute the value of vx in the expression. So we have this terms here. Now I'm going to solve this. Here you can see cancellation, certain cancellation here. And this turns out to be n naught e squared by epsilon naught m, n naught e squared by epsilon naught m. So I'm going to write it instead of this here, the plasma frequency, that is omega p square and iota omega p square minus, similarly minus iota omega p square. Now we are going to solve these equations to get certain expressions for Ex and Ey. And here you can see that I can take it here, and from this equation I can write okay. So and then I can write it in a bit. Here you can see iota and iota square minus and minus plus, and I can take it back here. So I have omega square minus omega c square and minus omega p square with ex, and then here minus iota omega p square with this term, and I can take it here, plus iota omega p square omega c by omega p y. So that's my first equation, and then from this equation I can write a similar kind of expression. That is, if I take this term here, omega square okay, I will write it down for you instead of omega square minus c square k square 1 minus omega c square by omega square, and then again we have this term here, iota omega p square, and this iota square minus and minus plus, this omega p square is going to come here, minus omega p square ey minus iota omega p square omega c by omega ex equal 0. Now you can see these are two simultaneous equations for Ex and Ey, and we can find a solution of these types of equations if I can write it in this way. Some A, B, C, and D, Ex and Ey equals 0. So I can write this equation in this term. Now this is valid only if we have the determinant of this matrix equals to 0. So here this is my A. I have to write Ex here and Ey here. So this is going to be my B. This is going to be my B, and this is C. So because this will come here and this will, I can write it in some other color that you can easily see. And so this is my equation A. This is my B. This will be my D, and this will be my C. So now keep it in mind that we are going to solve these terms, and by taking the determinant of this matrix equals to 0. Okay, now in order to keep that determinant equals 0, so we have AD equals BC. Now from the as we already know what A, D, and B, and C. So I'm going to write omega square minus omega C square, omega B square, omega square minus omega C square minus omega B square minus C square K square 1 minus omega C square by omega square, and this is all equal to omega B square omega C by omega whole square. Now this is the expression that we are going to solve for omega, or you can say that what we are looking for, that I'm going to get an expression for C square K square by omega square, which is basically C square by V phi square, or you can say the refractive index square. So I'm looking for this expression. So from this term, I'm going to separate out C square K square by omega square, which you can see is going to be appear here. But if I take it here and omega square. So I'm going to separate out this term and solve this C square K square by omega square in terms of omega. And then here we are going to find out certain specific values of omegas that are really important in the discussion of these waves in class. So I'm going to separate out this term. So you can see that if I take this term out here, so this is something like that: omega square minus omega C square minus omega P square minus C square K square by omega square. This is a basic algebraic exercise, and you can do it in many ways. And now I'm going to separate out this term and take it out here. So C square K square by omega square equals, this will go here and this will come here. So omega square minus omega C square minus omega B square minus omega B square omega C by omega square whole divided by this term. Now, in order to simplify this expression, and I'm going to divide this term with this and then separate out with this. So this turns out to be 1 minus omega p squared by minus this is what we will get. Now I'm going to solve this one and then try to find out the expression. Now let's take the we have c square k square by omega square equals 1 minus. Now I'm solving these two terms. P4 omega c square by omega square. Okay, now again solving the above, I will get this omega square minus omega p4 omega c square divided by. Okay, now I'm going to take omega p square over omega square out of this equation. So we have 1 minus omega p square by omega square minus omega c square minus omega p square minus omega p square omega c square divided by. Now I can solve this as omega square minus omega c square, and you can see if I take omega p square common, and I'm going to get this expression. Okay. Now you can easily see this omega square minus omega c square is going to cancel out here, and we are left with omega square minus omega p square divided by this time. So instead of all this, I'm going to write it here. This is the final dispersion relation for the extraordinary waves, that are the electromagnetic waves moving perpendicular to D naught with the electric field component polarized in both x and y direction.